As previously demonstrated, the history of science is a history of unifying ideas that requires both a deep understanding of logic and skillful observation. A review of that history will be necessary as we approach the challenges that mystify the greatest minds of the 20th century. The history of science is marked by two important principles, the principle of parsimony and the correspondence principle. Now, the principle of parsimony came into focus under William of Ockham, who asserted that given two possible explanations for any natural phenomenon, the one requiring the fewest assumptions is best. Where two things suffice as an explanation, three things are unnecessary. We can also call this the principle of economy underlying the conservation laws, later inspired by Antoine Lavoisier. In assuming the Earth to be the fixed center of the universe, Ptolemy needed everything in the night sky to revolve on an invisible axis, or epicycle, to explain their retrograde motions. Comparing the Earth-centered model of the universe to the Sun-centered model of the universe under this principle allowed Copernicus to remove the 90 epicycles of Ptolemy's model and replace them with just one assumption: the Earth orbits the Sun. This greatly simplified our understanding of the universe and our place in it, but was up against a much older way of thinking and couldn't explain why we don't feel the movement of the Earth. The answer to that question would have to wait for Galileo, who observed that we only ever notice changes in motion. It just seemed more natural to believe in a fixed stationary Earth and go from there. Galileo showed that steady, uniform motion feels the same as resting, and anyone in today's world knows this when sudden changes in speed and direction disturb our naps on long car rides. As clear and concise as Galileo's arguments were, however, he was still up against centuries of conventional wisdom and the authority of the church and state. Now, the correspondence principle states that the current paradigm or worldview, as expressed under conventional wisdom, can only be replaced by a new worldview that explains everything the current worldview explains, as well as the anomalies that the current worldview cannot even begin to address. In the case of the Copernican revolution, the sun-centered model meant that the movement of the planets could be understood independently of which planet or star you might be observing from, while the Earth-centered model would only hold true from the perspective of the Earth. Inhabitants on each planet would have their own unique perspective of how the celestial orbs move. The sun, stars, and planets would move very differently for them than for an earthbound observer. To them, they would all think they were the center of the universe, and the epicycles they observe would be very different from the epicycles Ptolemy observed. The sun-centered model does not suffer this flaw. We, of course, know now that not even the sun is the center of the universe, but that is a question for another time. Between Copernicus and Kepler, it was possible to imagine a solar system that worked no matter which planet or star you were observing from. It therefore defeated the Earth-centered model by virtue of its correspondence to the data, and Copernicus, Kepler, and Galileo became the shoulders on which Newton would stand. Although we take much of classical physics for granted in today's world, Newton's accomplishment was nothing less than Moses parting the Red Sea. It was the linchpin that seemed to have made all things possible and launched the Industrial Revolution. Not only was it useful, but it came to be regarded as descriptive of the universe more generally. As famously stated by Pierre-Simon Laplace, we may regard the present state of the universe as the effect of its past and the cause of its future. An intellect which at a certain moment would know all forces that set nature in motion and all positions of all items of which nature is composed, if this intellect were also vast enough to submit these data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. Only gradually over time did scientists start running into minor anomalies in nature that defied easy explanation under Newton's laws. Newton himself was well aware that there were many things his laws could not explain, at least not yet. Among these was the nature of light. He had cleverly used a glass prism to separate white light into the visible spectrum, and another prism to recombine the colors back into white light. He debated with Christian Huygens over the nature of light. Huygens believed light was fundamentally wave-like, while Newton proposed that light was fundamentally particle-like, or corpuscular, as he called it. Much like Bohr's and Einstein's debate, this one would also not be resolved in their lifetime. It would still be a century before Thomas Young would seek to resolve that debate in what is now the famous double-slit experiment from 1801. That experiment involved shining uniform white light on a barrier having two very tiny slits. This would turn one source of light into two sources shown against a wall. Just like waves of water, waves of light produce crests and valleys, and this would be the invention of the first interferometer or interference meter. Young's experiment produced alternating bands of light and dark lines on the wall, which is easier to explain if light is wave-like. As waves of light propagate, they form an interference pattern, where waves that are in phase reinforce one another, and waves that are out of phase cancel one another out. Young's experiment seemed to have decisively resolved the debate in Huygens' favor for the remainder of the century. Further examination, however, exposed that this conclusion was premature. There was still much to the nature of light to be discovered, and only a few short years later, more experiments were conducted when William Hyde Wollaston and Joseph von Fraunhofer developed the science of spectroscopy, where these very strange dark lines could be found at specific points in the visible spectrum of light. It was only later realized that these narrow bands of missing color were the signature absorption lines of various chemical elements. Physical objects could not only emit and reflect light, but also absorb it, and this made it possible to identify elements at extreme distances, even in the stars. The 19th century saw a flurry of scientific discoveries at the boundaries where Newton's laws no longer seemed to hold true, but the possibilities under those laws had not yet been exhausted. There were many technological innovations, and even today we accept his laws as a common sense description of the universe more generally. In Part 3, we will look more closely at the problems scientists faced as we approach the 20th century.